This video covers key strategies and knowledge that will make working in R much easier in the near and long term. Let's start by opening R. If we want, we can type directly into the console. However, this makes it a bit difficult to recreate our work, so it's helpful to open a new R document, also called an R script. We can open a script by holding down Command and hitting N. Whenever you write R commands, you should write them in an R script. Then you can send the commands in your script to an R console to be run. For example, if your cursor is on a line in the R script, you can run that line of code in the console by holding down Command and hitting Return. To run a larger block of code, highlight the code, hold down Command, and hit Return. It is useful to type your commands into an R script because you can organize your commands, and you can run and rerun these commands quickly and easily. You can also save an R script so you can use it later, and this makes it easy to pick up where you left off in your next work session. Here, I'll save my script to the desktop with the name temp.r. Saving and loading files in R can be very helpful. R is always looking in a particular folder on your computer, and it is sometimes important to know where it is looking so you can access and save files. There are two tools that will make this easier: getWD and setWD, which stand for Get Working Directory and Set Working Directory. The getWD function will tell you which directory R is currently working from. If you'd like to change the directory you're working in, use the setWD function and specify a file path inside the parentheses, where the path is contained in quotation marks. For those working in OS X, there's one more tool, Command D. Typing Command D will open a window where you can navigate to a folder of your choosing. When you are done in an R session, save your script and then type Q open parenthesis close parenthesis into the console. As long as you carefully document your work in an R script, there's little reason to save your workspace. In the next video, we'll begin creating objects in R. To get acquainted with R, let's do some basic calculations. We can add numbers, multiply numbers, and we can invoke built-in functions to do more complex calculations. So R is good at calculations, but we don't want to type in all of our data. Instead, we'll often store our data into R objects. In a later video, we'll load in larger data objects, but for now, let's create some simple R objects. Let's save the value 4 to an object called x. Usually we use a less than symbol followed by a dash to communicate that we want to save something, like a number, into an R object. Now we can use x to do some basic calculations. For example, x times x. Or we can calculate the square root of x. Note that sometimes people might call x a variable. So think of the terms object and variable as meaning the same thing in R. The names of R objects can include letters, numbers, underscores, and periods. However, the name should always start with a letter, usually one that is lowercase. If you'll be sharing your code with others, check with your group to see if there's a style guide that you should follow for your R code. One last tip. If you want to review an earlier command you made, click the command line on the R console and then hit the up arrow on your keyboard. When you do this, you will be able to see earlier commands you have run and, if you desire, you can rerun them. In the next video, we'll create and work with vectors in R. One of the fundamental objects in R is a vector, which is just a term to mean a single set of values in a particular order. We can create a simple vector in R using the concatenate function, which is a function represented by a lowercase c. Inside the parentheses, we put values or other vectors separated by commas, and these will be stuck together to create a new vector. When we print the vector, R simply prints the values one after another. You might wonder, what happens if there are so many values in the vector that it hits the end of the line? Well, the values wrap to the next line, just like the text would if you were writing a paragraph. Notice that there's also a little extra information in the first and second lines. In the first line, we have a number 1 in brackets, and on the second line, we have a number 10 in brackets. In each case, these correspond to how far r is into the vector at the start of each line. For example, the 10 indicates the first element on the second line is the 10th element of the vector. The 1 in the brackets at the start of the output indicates that this line was the start of the printed vector. This brings up a subtle point. Looking back on our earlier output, we can see the bracket 1 in each output. While each earlier output looked like a scalar, that is, a standalone number, each of these is really a vector with a single value. In R, a vector of length 1 is equivalent to a scalar. For those vectors with length greater than 1, it is common for us to want to access a specific element. Let's call our longer vector v. If we wanted to look at just the first element of v, we use brackets with a 1. Or if we wanted the third value, we could use a 3 in the brackets. We can also request several values at once. To do so, we create a vector that indicates the positions of the values we want returned. Then we put this vector into the brackets. So let's suppose we want to look at the first 3 values. We start by creating a vector 1, 2, 3. Here I've done that using the special notation 1:3, which produces a vector with values 1, 2, 3. I'll save this vector into a variable called lookat, and then I'll use lookat inside the brackets to get at the first 3 values of v. There are 3 more functions worth remembering when it comes to vectors: length, head, and tail. The length function indicates the number of elements in a vector. The head function returns the first 6 observations in the vector, and the tail function returns the last 6 observations in the vector. Here's v printed out for a comparison. Also, if we want, we can specify a second argument in the head or tail functions. This second argument says how many observations we want to see. For example, here I'll specify that I want to see just the last 3 values of v using the tail function with 3 as the second argument. In the next video, we'll work with character and Boolean vectors. R can handle a lot more than numbers. For example, it can handle character objects, which are also known as strings. We can make a simple character object just by putting some text in quotation marks. You might notice something we saw before, which is that the output is again preceded by a 1 in brackets. This character object is a vector, and we can create a longer vector using the concatenate function. As with numeric vectors, we can apply functions to a character vector to learn more about it or get summary information. In addition to the numeric and character type of vector, we can create a Boolean vector. In the simplest case, we can write true in all caps, or we can write false in all caps. We can also create a vector of true and false values using the concatenate function. One of the really handy features of Boolean vectors is that they can be used to extract specific elements of a vector that meet a certain criteria. For example, here I'll use the nchar function to find out the number of characters in each character string in the vector. Then we're going to create a new vector called under 10. This vector will indicate which elements of v have less than 10 characters. Finally, I can subset v using under 10. In the next video, we'll start doing arithmetic with vectors. The simplest type of vector arithmetic in R is just adding a number to a vector. Let's create a vector v of values 10, 20, 30, 40, 50, and 60. Then we'll add 1 to this vector. When we add a single number to a vector, it adds that number to each element of the vector. We can also do simple multiplication, which works in the same way. Things get a little trickier when we multiply two vectors where each are longer than length 1. Let's create a second vector called w that takes values 2, 3, 4, 5, 6, and 7. I've constructed this vector using a special notation of 2:7, which generates a sequence of integers 2 through 7. This is a handy way to create a sequence of all integers between two values. Let's multiply v and w. Is that what you expected? R performs element-wise vector multiplication. That is, it'll take the first value in each vector and multiply them. Then it'll take the second value from each vector and multiply those, and so on. When working with vectors, R works in the same way when doing addition, subtraction, division, and other basic operations. Things get a little more confusing when we multiply vectors of different lengths. Let's overwrite w with a vector of length 2 that takes values 5 and 10. When we multiply v and w now, the result might be surprising. We get another vector with 6 elements. Let's take a closer look at what happened. The first two values make sense. They are again the element-wise multiplication. However, when we get to the third value, it appears to be the product of the third value of v and the first value of w. The fourth value is the product of the last value of v and the second value of w. What we've just observed is that R recycled the vector w so that it could complete the multiplication across the full length of v. It also did so without any warning or error. R is built to recycle vectors, and it doesn't always tell you when it does so. Let's do one more vector multiplication. We'll overwrite w one more time, and make it a vector of length 4 with values 5, 10, 15, and 20. Here this vector has been created using the sequence function. The first argument says where the sequence starts, the second where the sequence should end, and the third how big of jumps to take to get from the first to the last value. Here again, we multiply out v and w. R again will recycle w, but this time it gives us a warning. In this case, when R recycled w, it still had elements left over when it ran out of elements with v, so it wanted to make sure that we are aware of this. There are several ways we can perform arithmetic in R using vectors. We can raise every element in a vector to a power, or a different power for each element. Here I've again used the integer colon integer notation to create a vector of values 2, 3, 4, 5, 6, 7. Many functions also work nicely across vectors, such as the square root function. In the next video, we'll learn about matrices. Matrices are just slightly more complicated than vectors. To create a matrix, we usually start by creating a vector. Here, I'll create a vector that has elements 1 through 12 using the integer colon integer notation. Next, I'll use the matrix function to create the matrix. Whenever creating a matrix, it is helpful to provide the number of rows and the number of columns to ensure that you're creating the precise matrix you expect. You can do this using the n-row and n-col arguments. If you happen to forget to use the argument names, R will try to guess what you meant. It usually does this based on the order of the arguments. For the matrix function, if we specify the number of rows before the number of columns, we get the same type of result. You can also experiment with leaving off one of the arguments. Notice that if I only include the number of columns, I need to specify the n-col argument name if I want to get the same matrix that I got before. The matrix function is very handy in that, while you might specify the complete set of data for the matrix right up front, you don't always have to do this, if parts of the matrix will repeat. Here's a matrix with all zeros. We only need to specify a single zero for the entire matrix. We can also specify a partial vector that can be used to fill in the entire matrix. Let's create a 3x4 matrix with values 11, 12, and 13 filled in the entire matrix. In this example, the vector, which had length 3, was recycled until the 3 by 4 matrix was filled up. Notice that the vector runs down the columns rather than across the rows. If we had wanted to make it run across the rows, we can add a fourth argument to the matrix function. By row equals true. We also sometimes want to learn more about a matrix. We might start using the dim function to learn the dimensions of the matrix. Here, the output of dim is a vector of length 2. The first value is the number of rows in the matrix, and the second is the number of columns. We can also apply the length, head, and tail functions to a matrix. The length will return the number of elements in the entire matrix, and the head and tail functions will provide up to 6 rows from the top and bottom of the matrix. If we want, we can specify a second argument in the head or tail function to get a different number of rows back. One last matrix topic to consider is how to select one or more elements of the matrix. Let's return to the matrix that we had at the beginning of the video. Here, it's just values 1 through 12 in the matrix that has 3 rows and 4 columns. Like with vectors, we can subset a matrix to select one or more parts of the matrix. But since a matrix is two-dimensional, we need to specify 2 dimensions in the brackets. For example, if we use 2, 4, we will get the element in the second row and the 4th column. If we leave the column entry blank, we'll get all of the columns, and if we leave the rows blank, we get all of the rows. Just like with vectors, you can use vectors of length greater than 1 inside the subsetting to return more than one value. Using vectors with length greater than 1 to get both rows and columns may produce a slightly surprising result, another matrix. Let's consider the matrix where we specify the rows 1 and 2 and the columns 3 and 4. Doing so gives us back a submatrix specified by these dimensions. Finally, before moving on, one final word on matrix subsetting. If you forget the comma, R will still return a value. Each matrix is stored in R as a vector with extra dimensions. So if we request the third element of the matrix, it counts down the first column and returns the third element. If we specify the 5th element, R runs out in the first column and so goes to the second column as it keeps counting. I wanted to highlight this not because subsetting in this way is a good idea, but just to make clear that it can be accidentally done, and so it's something you need to watch out for. Using the row-column subsetting notation is the preferred method. In the next video, we'll take a look back at the first 6 videos, and also how to access help files for functions inside of R. Functions are special R objects that take in other objects as arguments and produce something. In many cases, the person who wrote the function provides default values for some or even all of the arguments. We've now seen a couple important functions and techniques. First, we saw the concatenate function that was used to create vectors. And we saw we could create vectors that are sequences of integers using the integer, integer notation. We used the length, head, and tail functions to learn more about vectors. We also saw character vectors. The letters object is a built-in vector of letters inside of R, and if we wanted, we could examine a subset of the letters. We also saw how to construct matrices using the matrix function, as well as how to specify the number of rows and columns for a matrix using the second and third arguments. The dim function provided a way to check the dimensions of a matrix, and we could again use brackets to examine a subset of the matrix, except that we specified both rows and columns, or just one. Videos are great, but they're no stand-in for documentation. Thankfully, most functions in R are very well documented. To access the help file for a function, just type a question mark, the function name, and then hit return. Here's the help file for the sequence function. At the top of the file is a description of the sequence function and other related functions described in this help file. The next section shows the sequence function and its variants, and the arguments section provides details for what type of inputs are reasonable and how to specify additional options. The next sections of particular interest are the See Also and Examples sections. It's a good idea to take a look at the example section early on when you're exploring a new function. On OS X, it's also easy to run examples from the help file by highlighting the example text, holding down Command, and then hitting Return. Congratulations! You've completed the first section of R videos. Take some time to try out what you've learned, and when R gives you an error, check for typing mistakes, which are common. After you've finished experimenting, fuel up and start Section 2. Welcome to Section 2. R is a powerful tool for data analysis, and the first step to working with data in R is to get the data into R. Suppose I have a CSV file on my computer and I want to load it into R. Since I'm running R on OS X, I could use the Command D trick to change my working directory to the folder with the file, but it's also helpful to know how to navigate using the getWD and setWD functions. We'll also make use of the list files function, which lists the files and folders in the current working directory. I want to get into my Google Drive folder, so I'm going to specify that in the setWD function. Next, I'm going to print out the folders in this Google Drive folder and navigate to projects. Next, I'm going to navigate to the top secret folder, and since I know there's a data folder there, I'm just going to add this folder into my setWD command. Alright, I've arrived and I can now see the dataset of interest in my current working directory, the state.csv dataset. Since I'll be saving this code, I might as well save my current working directory in a setWD command at the top of my script. This way I won't need to set the directory in the future unless I change the working directory of my project files. Now that I'm ready to go, I'll load in the state.csv file using the readCSV function, specifying the name of the file in quotation marks. When you're reading a CSV file into R, it's stored as a data matrix, which is more formally called a data frame in R. Just like with a regular matrix, I can use the dim function to see how many rows and columns are in the dataset. There are 51 rows representing all US states and Washington, D.C., and 12 different columns representing the 12 different variables recorded for each state. I'll use the head function to print out the first 2 rows of the state dataset, just like I could do with a regular matrix. However, if I apply the length function, R will just return the number of variables in the dataset, which are represented by the columns. Data frames are one of the most common objects for holding data inside of R, and I can subset on them in ways similar to how I might subset a matrix. This is fine, but there are actually better ways with data frames. A new function for data frames worth remembering is the names function, which is used to access the variable names. Once you know the names of the variables, it's easy to extract out the entire variable using the dataset name, followed by $, then followed by the variable name. Let's take a look at the smoke variable. The smoke variable is a numerical variable representing the percentage of people who smoke in each state. If I wanted, I could apply some standard functions like the mean or standard deviation function to get some summary information about this variable. In addition to subsetting with brackets, I can make use of the subset function. Here I'm going to examine only states with smoking rates higher than 25%. If I wanted, I could also specify that I only want to select a small number of columns. Next, I'll take a look at the party that won each state in the 2012 presidential election. This is in the press12 variable. Note that the press12 variable isn't numerical, yet it was stored with the smoke variable, which was a numerical object, in the state data frame. Data frames can hold a different type of variable in each column, while a matrix can only hold a single data type for the entire matrix. Notice also that the output doesn't look like a regular string output, which generally has quotation marks when it is printed out. Additionally, there's a listing at the bottom that indicates there are 2 levels. Output like this indicates that this is a factor variable, or a factor object. A factor object is a special kind of object that's sort of a blend between character and numerical variables. If you ever have substantial trouble working with factors in R, you can just convert the factor to a string with the as character function. R will generally convert a character variable back into a factor variable when it is appropriate to do so. However, when R does do this conversion, it may notify you with a warning. Just read your warnings carefully and make sure that that's all that's happening. In the next video, we'll talk about ways to take a quick look at a data object inside of R, and we'll also take a look at date objects. There are two other functions I'll consider that provide a brief overview of a data frame. But first, I'll load in a dataset. This time, stock market data. I've already navigated to the proper folder, and I can see the file in my current working directory if I use the list files function. This particular dataset is saved as a tab-delimited text file. So to import it into R, I'm going to use the readDelim function. In the last video we saw how to load in CSV files, and in this video we've seen now how to load in tab-delimited files. If you aren't sure how to load in your particular dataset, Google your question. There are many online resources about loading data into R that are likely to be very useful. Alright, back to the dataset. I'll take a look at the first and the last three rows. I can also get a better overview of the dataset by using the str function that provides a breakdown of the object's structure. Here I can see that stocks is an object with over 70,000 rows and 8 variables. I can also see each of the names of each of the variables, and the first several observations to get a sense of what each contains. Note that observations for factor variables may look like numerical variables. Another helpful function to get an alternative look at an R object is the summary function. In the case of a data frame, the summary object returns a summary of each column. Notice that there are NA values represented in some of the columns. In R, NA means that there's a missing observation, and here it lists the number of missing observations for each of these columns. Note that the str and summary functions are not specific to data frames. They can be applied to any R object to get a quick peek about the object and its characteristics. You might have noticed that one of the variables in the stock dataset is a date. I'm going to take a closer look at the date and print out the first 20 values. If I look carefully, I can see there's also a levels attribute associated with these dates. That means that R has interpreted this field as being a factor. It would be much more useful to keep this as an actual date object. In this case, the dates are formatted as day, month, and year. And in such cases, I want to examine this variable as a date object using the asDate function. I also need to specify the format of the date. There are many different ways to format dates, so you may need to look up how to specify the date formats you run into. For this purpose, you'll probably want to look in the strp time function help file. You can do this by typing $strp time and hitting enter. I'm going to save the formatted dates in an object called s.date. While having this date object is helpful, I really would like to replace the original date object with this one. In fact, it actually would have been much easier had I just skipped the step of creating sdate and just saved the modified version over the date object right from the start. Now if I look at the stock objects again with the head function, I can see that the date variable is now formatted in a standard way, starting with all 4 digits of the year, then the next 2 digits for the month, and then the last 2 digits being the days. You might wonder, why go to all this trouble to format the date? Why not just leave it as a factor, or just set it as a character? First, you might like to examine the differences of dates to learn the proximity of 2 observations to each other. Second, if you generate a time series plot that makes use of the date object, R will do its part to help make the plot look nice. For example, here I'll plot the time series of the stock price for Google. I'm specifying the date as a variable for the horizontal axis, and since this is formatted as a date, R will use this information and plot the years all along the axes. Had I not converted the date over to a date object, the plot wouldn't have looked nearly as nice. There are several other reasons to properly process and format dates in R, but the general reason is that doing so communicates the data structure accurately, and this will make it easier for you and others to use and reuse your code. In the next video, we'll talk about if statements and also the which function. In this video, I'll cover 2 important structures in any language, the if statement and logical operators. I'll also introduce the if-else and which functions. I'm going to occasionally rely on the stock data used in the last video, But to keep things simple, I'm also going to omit any rows that have an NA value, as these represent missing observations in the data. An if statement is used to execute some section of code on the condition that a particular statement is true. In this setup, the code inside the braces will run if the condition is true. For example, suppose I want to check whether the first entry in the stock data was up or down. If it was up, I want to create a variable called status that takes the value up. It would also be informative to label the status as down if the stock is down, so I'll add an else statement. The code in the second set of braces will execute if the condition is false. However, this still isn't quite right. What if the stock opens and closes at the same price? I can add a condition for the second set of code using a second if statement after the else command. Then I'll add another else command at the end that labels status with a value of flat if the stock is flat for the day. I also want to briefly mention the if-else function, which could be used in this context to create an up, down, flat vector for all the elements in the stocks data in just a few lines of code. The if-else function takes 3 arguments: a vector of length 1 or more that contains true and false values, a value to take for each true instance, and a value to take for each false instance. Though this still isn't quite right because I need to return a value of down if the close is lower than the open. I can do this by creating a second condition and adding one more if-else command. Here I've done something subtle. I've provided the status argument for those cases where the close is not lower than the open. I've exploited a special feature of the if-else function, which is that when a vector of length greater than 1 is provided in the second or third arguments, if-else will be performed element-wise for that argument. I'll leave it to you to verify that this code works and why it works. You should think about each possible case. A stock can be up, down, or flat, and I strongly recommend you create some test data and work your way through each step of the code. Next, I want to talk about logical operators. I'm going to create a vector with 10 random integers between -1 and 13, and a second vector in the same way. I'd like to know whether all the elements in x are greater than 0. I might intuitively start by using the command x greater than 0. However, as R does in many other scenarios, it also performs this check element-wise. Here you can see I have a vector of true and false values, but I can use the all function around x greater than 0 to answer the question as to whether all of the values of x are greater than 0. We can also check other things, such as, do any elements of x line up with those in y? This again returns a vector of true and false, but this time I can use the any function to check whether any of the values are equal. We can also do other checks that relate x and y. For example, consider the separate commands x greater than 0 and y greater than 0. If I wanted to check in which elements this was true in both vectors, I could use a single ampersand between the commands. Here, the single ampersand means to check whether both the first and the second condition are true on an element-wise basis. There's a similar OR command using a pipe or a vertical line character that creates an element-wise basis on whether one statement or the other statement is true. R, like other languages, also has a double ampersand and double pipe notation, though I'm going to move on. If you're interested in this, you should check out the help file for XOR. The last topic I wanted to cover in this video is the which function, used to identify which elements or observations satisfy a particular condition. For example, I'd like to know which observations had a big intraday fluctuation. To begin, I'll create an object called fluctuation that gives the raw intraday fluctuation. I can scale the fluctuation by dividing the difference by the opening share price of the day. Next, I'll create a condition for whether the fluctuation was greater than, say, 25%. This is a Boolean vector of true and false values that report whether each row in the data frame satisfied or did not satisfy this big fluctuation condition. If I wanted a vector reporting just those rows that satisfy the condition, I can use the which function. These rows represent observations where the stock price fluctuated by more than 25% in a day. If I wanted, I could examine each of these rows in the original dataset. In the next video, I'll talk about for loops. Our second key programming tool is the for loop. A for loop is a structure used to execute a set of code repeatedly. The for loop statement specifies an index over which the loop is computed. For example, here I'll execute a for loop using an index called I. The object I will start the loop by taking the first value in the 1 through 10 vector. That is, to start, I will equal 1. Next, the for loop will execute. Then I will take the next value in this vector, which is 2, and the loop will execute again. This will continue until I has taken the last value in the vector, 10, and the code executes one last time. In this set of code, the value I squared will be appended to the vector x using the append function. Here I got an error. I'll take a closer look. I can see that x never actually existed, so there is no way to append anything onto the first iteration. To fix this, I'll just initialize x as an empty vector using the concatenate function, but leaving the arguments empty. Okay, this runs well. Look at x. In each iteration, a value of I squared was appended to the end of x. So the first element was created when I was 1, the second when I was 2, and so on. Okay, I've done something pretty cool here. I've done 10 calculations using a for loop, and it wouldn't be hard to do many more with the same set of code. For example, I could easily go from 1 to 100 rather than just 1 to 10. While there are other better ways to do this particular calculation, there are instances where a for loop is very useful. Alright, one more look at the stock data. To calculate the smallest and largest values for each stock in the stock dataset, I'm going to start by creating an object called the tickers. That is just a list of the unique stock tickers in the data. Since for loops can iterate over any vector, I will write a for loop to iterate over the object that I've called the tickers. It's sometimes helpful to also give a meaningful name to the index, so I'm going to change the index I to ticker. Now I need to create code for the general case. For a given ticker, calculate both the low and the high value. I'll start by identifying which rows are of interest in the stocks dataset. The vector called lookAt is a Boolean vector indicating which observations represent the ticker for the given iteration. Next, I can create two statements to calculate the lowest low and highest high of these observations. Finally, I need to store these values somehow. I can start by initializing two objects, lows and highs. Next, I can use an append command to append a value onto the end of the vector. Alright, I can run the code and print the results. But something's wrong. Well, I'd want to spot check some of my data anyways. Something bad has happened. A value of NA in R means that a value is missing. And more generally, oftentimes functions will return NA if any of the observations are missing. If I took a look through our dataset, I'd find that there are several observations with missing NA values. Here I've checked how many entries in the column low of the stocks dataset are missing. In many functions, such as min and max, there's an optional extra argument that is useful for ignoring missing data, the na.rm argument, which I'll set to true in the min and max functions. Now when I rerun the code, I get sensible results. I'd want to look at the data more carefully to see why some observations are missing, but I'll leave this as a topic for another set of videos. One final word. Even in this example, there are other better functions that could have been used to get the same results much more quickly. This would be important for code that should be implemented efficiently, and I'll get to these functions in the future. However, for the beginning R programmer, it's sometimes easier and clearer to simply implement a for loop. Lists are a special type of object that hold other objects. I can initialize a list by simply using the list function. I can create items in the list by providing arguments to the list function. What is important to understand is that a list can hold objects of all different types. In this example, the first object is a numerical vector of length 5. The second object is a character vector of length 1, and the third object is a Boolean vector of length 1. If I wanted to access an item, I use the subsetting with double bracket. I can also add on new items, even providing the character name for the item. When a list has named objects, those objects can be accessed using a special $sign notation that is reminiscent of the same notation for data frames. Lists also aren't restrained to holding just vectors. They can also hold matrices, data frames, and even other lists. Lists are so powerful since they create helpful ways to organize diverse sets of data or results. Oftentimes I have many groups of data, and it would be helpful to calculate statistics for each. I might organize these statistics using a list. I'm going to load in the stock data just as we have in the last couple of videos. And my goal will be to create a summary of the prices for each stock. I'm going to do this using a for loop. The first line in the for loop will identify the rows of interest. The second line will calculate the summary and store it in an object called stock summary. I also shouldn't forget to initialize the stock summary object, here as a list. Finally, I can take a look at the results. Not surprisingly, there's a lot to look at. If I wanted, I could look at a specific summary for a particular stock, say Google's stock. What I have done here in just 6 lines of code is very powerful. I've calculated summaries for every stock in the dataset, and this code works regardless of if I have 5 stocks or 5,000 stocks. In other instances, I might choose to do something even more complex, like fit a linear model to the data for each stock separately. Even in that complex case, a list can be used to store the result. I noted in the last video that as you become more familiar with R, you'll find out that there are more helpful functions to do operations commonly done in for loops. This is also true with this example, which could have been written much more compactly using some additional functions. Some of these functions we'll encounter in the next section, like the functions by and apply. Great work on making it through the second section of videos. Take a short coffee break, practice what you've seen, and then get started on the third section. Writing your code into R scripts is valuable for managing and organizing R objects. But sometimes you may wish to clear some objects from your workspace. To get a look at what objects exist in your current workspace, use the ls function. If you want to remove an object, use the remove function with the argument name as the object to be removed. If you want to remove all the objects in your workspace, you can use the list argument in the remove function and specify all the objects in the workspace using the ls function. It's also helpful to be able to easily convert between objects of different types. We'll consider 3 functions for converting objects to numerical, character, and factor object types. For instance, we can apply each of these functions to the object x. Applying the as character and the as factor functions affect the outcome. Had I wanted to actually change x to, say, a factor, I could have assigned the new result to x. One special note here. If you have a factor variable that also looks numeric, always convert it to a character before converting it to a numerical value. There are other comparable functions that you may occasionally find useful, such as matrix, as data frame, and as list. One last function I'll consider in this video is the unlist function. In the usual process of data analysis, I might create a list to hold summary results of an experiment. Here, I'll construct a list manually for 4 groups. In this example, you can think of the first number for a group to represent its corresponding sample size. The second number might represent the average response for that group, and the third value might represent the standard deviation for the group. Just a side note worth mentioning. I typically perform these types of calculations in an automated way, which would make it easier for the code to be scaled to an arbitrary number of groups. If you need a refresher on this topic, look back to the 5th video in section 2. Alright, so the results are stored in a list where each list item represents the results for a single group. If I unlist this object, I get a vector of the unlisted results. It would actually be more useful to hold this object as a matrix or as a data frame. So I'll form these unlisted results into a matrix. If I'd prefer a data frame, I could use the asDataFrame function applied to this matrix. If I wanted, I could also adjust the column names of the data frame using the names or the column names function. In the next video, we'll explore the family of apply functions, which are helpful for applying a function across the rows or columns of a matrix, or across the elements of a list. The apply function and its variants are useful for applying a function across an R object. We'll consider two variants of these special class of functions, apply and tapply, and we'll also look at the by function. I'm going to start by loading in a new dataset, website revenue for the month of March for 10 businesses. I've used the argument header equals false because there are no column names stored in this comma-separated values file. The data in this data matrix have been stored in a slightly unorthodox way. Each business is represented as a column, and each row represents a day in order of March 1st through March 31st. So, for example, on March 3rd, the 10th business made $23.98. It might be helpful for me to take a quick look at how the businesses are doing by taking a look at their total revenue. I could take the sum for each column using a for loop and store that result in a vector, but this would actually be inefficient. Instead, I should use the apply function, which will be more compact and also run faster with larger datasets. The apply function is useful for applying a function across either the rows or columns of a data matrix. That is, I might want to apply a function across each row separately or across each column separately. The first argument is the data matrix itself. The second argument is the dimension number over which to apply the function. Rows are represented by number 1 and columns by number 2. Think of the second argument as specifying the dimension that you actually want to retain. The last argument is the function to be applied. In a similar way, we can also compute the total revenue for all the companies on each day of the month by applying the sum function over each of the rows. Notice that there are some missing observations. If we would look into the data more carefully, we would find that there are two missing values, each in the third column. If we know that it's okay to omit these data, we can tell the sum function to ignore the missing observations using na_remove equals true. The apply function passes this argument onto the sum function. Generally, any extra arguments to apply will be passed to the function you specify in the third argument. In this particular use case, we probably should want to investigate the missing observations rather than simply ignore them. Also, just a technical note, for this application of apply, I could have used either the callSums or rowSums functions. Alright, onwards to the second function, tapply. To help explain this new function, I'm going to load in a second dataset that summarizes eBay auctions for the Mario Kart video game for the Wii. This is a tab delimited text file of the data, so I'm going to read it in using read_delim. To keep things simple, let's focus on three variables: wheels, conditions, and total price. The tapply function is similar to the apply function in that it helps aggregate data efficiently. For instance, we could examine the sum of all of the total prices of auctions that were new and used separately by providing the vector for the total price as the first argument, the vector for the conditions as the second, and then the sum function as the third. Just like in apply, the third argument for the tapply function is another function to be applied across the data. However, in this case, the function is applied to each group, where the groups are specified by the second argument, which in this case is the condition of the game. I'm going to modify this command a little bit since it makes more sense to look at the average price of the game. As you might have anticipated, the games that are new tend to sell for more than the games that are used. Here, the difference is about $10. There's a second important variable in this application that relates to the price: the number of steering wheels that come with the game in the auction. These steering wheels are a game accessory that make playing Mario Kart a bit more fun. Let's look at the average price of the auctions with different numbers of wheels included. As you might expect, we again see a steady increase in price associated with having more wheels included in the auction, about $6 to $10 per wheel. Now, there's something interesting to think about here. If I consider the influence of both price and the number of wheels simultaneously, what will this do to the estimated cost of a new game versus a used game, and also the cost of an extra wheel? A table to look at the average price across each of the combinations of condition and wheels can be made using the tapply function. To do this, I'm going to provide the data frame with just the condition and the wheels columns as the second argument. Some of these numbers look a little bit surprising. For instance, going from no wheels to one wheel doesn't seem to influence the price when the game is new. If we dig in a little more, here using the length function in place of the mean function, I can see that one of the groups had very few observations, and so this average is probably less reliable, and this might explain the difference. If I was going to continue this analysis, I'd probably look into this some more. One last function before we wrap up. The by function is a variant of the tapply function, but by default, it returns a vector of the results. Note that when it is printed, it won't really look like a vector, though you could access the elements just as if it was a vector. In the next video, we'll take a look at three functions: with, within, and aggregate. In this video, I'll take a look at three functions: with, within, and aggregate. To explore these functions, I'm going to load in the Mario Kart dataset. The with function can be used to access variables in a data frame with ease. This is especially important when the name of the data frame is long and multiple variables are being accessed for a calculation. I can read this command as, with Mario Kart, compute the total price minus the shipping price. The within function is similar to with, except that it's used to create new columns and merge them with the original dataset. For instance, here I'll add an auction closing price to the data frame and store the result in a new data frame called MK. Notice that the commands to generate the new variables goes inside braces as the second argument. If I had wanted, I could have added multiple variables by creating more variables inside of the braces. As you can probably guess, the with function is useful for one-off calculations, while within is useful for expanding a dataset to include new variables. When I want to aggregate or summarize results, I often use the aggregate function. Here, I'll aggregate across the number of wheels and the condition variables. The first argument is a formula. The dot on the left side of the tilde means keep all of the variables for the output, and the variables on the right side, separated by a plus sign, indicate which variables to aggregate across. The second argument is a data frame, and the third argument is how to aggregate the variables. Had I only wanted to aggregate across one variable, say the total price, I could have replaced the dot with the total price variable. Notice the similarities between what the aggregate and tapply functions produce. Which you should use depends on what you will use the output for. Congratulations, you've finished section 3. The next section will introduce how to write your own functions. Building functions in R is a key skill that I'll cover in this section of videos. In this first video, the basic structure of a function will be introduced in the context of reporting both the mean and the standard error of a dataset. I'm going to start by creating a test dataset called D. Here, D is a sample of 25 observations from a Poisson distribution with 8 degrees of freedom. Next, I'd like to ensure that my test dataset is stable, so if I rerun my code, I'll get the same kind of results. I'm going to do this using the setSeed function. Now if I regenerate my data multiple times, I get the same test dataset. Now on to the general structure of a function. I'll start by carefully choosing a function name. Here I've thought about this ahead of time. I'm going to call it get, mean, and standard error. Next, I'll assign a function object to this name using the function declaration. I've provided a generic argument x to represent the data, and I'll use braces to contain the code to be executed using the arguments. I'll compute the mean, the length of the dataset, and the standard error of the mean inside of these braces. Presently, the function identifies the mean and its standard error. However, the variables m and SE only exist in the scope of the function, so when I run the function, I don't actually get any results. What I need to do is add a return statement. Now when I rerun the function, the mean and the standard error will be returned. This new function can be helpful, however, its present output isn't actually ideal. It would be nice to make explicitly clear what each of the outputs is from the function. In the next video, I'll expand the function and take a look at this challenge. The function in the last video is used to report the mean and the standard error. Suppose I wanted to also report a 95% confidence interval for the mean. Here I'll construct a confidence interval. The QT function is used to identify the 97.5th quantile of the t-distribution with n-1 degrees of freedom. There might be some temptation to concatenate the confidence interval with the current results being reported from the function. In some instances, this might be fine, but it isn't a very clear way to organize the results. For example, what if another user mistakenly thought the first two values were the confidence interval and the last two were the mean and the standard error? That could be disastrous. When multiple objects are being returned from a function, it's usually helpful to return them in a list. But even now, things might still be a little bit unclear. For this reason, it's useful to add names to each element of the list. And before I forget, I should update the name of the function. I'm going to name it getCI for getConfidenceInterval. There's one more change I want to make before moving on, making the function slightly more general by allowing for a different confidence level. I'm going to do this using a second argument called level. Since a 95% confidence level is so commonly used, I'll specify a 0.95 confidence level as the default. Next, I need to make some slight adjustments to the body of the function to make use of this new argument. I can compute the upper percentile for the confidence interval, then provide this as a substitute for 0.975. Now I can run the function without specifying the level to get a standard 95% confidence level. Or if I want a different confidence level, say 99%, I can easily make that request. Suppose a user input a value for a level of 99 rather than 0.99 for the level argument. In this application, it would be nice if the function failed elegantly and communicated why there was an error rather than simply reporting a warning. This will be the topic of the next video. Providing clear feedback to users is one part of building great functions. I'm going to take a look at the function from the last video that was used to compute a confidence interval for the mean using a sample of data. What if a user provided a percentage instead of a proportion for the confidence level? Currently, the user simply gets a warning, and the reason behind the warning isn't going to be obvious to new R users. Instead, it'd be helpful to stop the execution of the function and clearly communicate what is wrong. I'll do this by stopping the function if the level of the argument takes a value less than 0 or greater than 1. To stop the execution of a function and return an error, use the stop function. The argument of the stop function is a character string to communicate why the error was generated. Here, I'll communicate that the level variable should have been represented by a proportion between 0 and 1. Now, when a user inputs a level value that is invalid, it stops and returns an error. I'm also a little concerned that a user might provide a level that takes a value like 0.05 or 0.1. They might think they are supposed to provide a significance level rather than a confidence level. If the confidence level is smaller than 0.5, I'd like to warn the user that they should rethink their input. I can do this using the warning function. In the next video, I'll introduce how to pass an arbitrary number of arguments to a function. In this video, I'll cover how to pass arguments to existing functions inside of functions you are creating. To do so, I'll use the website revenue data highlighted in the last section. I'd like to create a function that summarizes the revenue and other objects like it. I'll call the function revSummary, and it'll take just one argument that should be a data frame or a matrix, where the rows represent days, columns represent different websites, and the entries represent revenue for the websites on each day. I'll build in a simple check to make sure that the data object comes in a form of a matrix or a data frame. If it doesn't, then I'll provide a suitable error. Next, I'll calculate two summaries. the average revenue per company and the average revenue per day for the companies. In a previous video, I used the apply function for this, but here I'll use two functions in R specifically built for taking the mean across rows and columns, row means and col means. I'll return those results in a list with two items that will be returned at the close of the function, mean revenue per company and mean revenue per day. Finally, I'll apply my new function to the revenue data. When I execute the function, I get a list back, as expected. However, there are some NA values that indicate that some data are missing. Here, I'll identify which observations in the revenue data are missing using the isNA function together with a which function and an additional argument, array index equals true. The first is for the 12th day and the third company. The second is for the 13th day and the third company. It's possible that some end users of this function, including myself, may occasionally want to have such observations omitted from the calculations in the functions using an NA argument, similar to how we've seen this argument used with other functions. However, this NA remove argument would need to be passed to both row means and col means. This is fine, but it's actually a little bit more generalizable to accept an arbitrary number of arguments to be passed to these functions. I can do this using an ellipsis in rev_summary's declaration. This allows the rev_summary function to accept extra arguments not specified in the function declaration. Next, I indicate which functions should receive these extra arguments. Since my intention here is to allow users to pass the NA remove argument to row means and col means, I will add an ellipsis to the end of each of these functions. Now, if I pass NA remove equals true into the rev_summary function, this argument will be passed to the row means and col means functions, which will then remove the NA values from the calculations. Note that if you want, you may access the arguments from the ellipsis in your function using the list function with an ellipsis as its argument. In this way, you may also write functions that allow for an arbitrary number of arguments and then access all of those arguments in a list. What's been covered in this video is how to easily pass additional arguments inside your functions and how to access those extra arguments using the list function. In the next video, I'll show how to hide function output that might flood a user's screen, and I'll also cover a useful tool for building recursive functions, which are functions that call themselves. In this video, I'll show how to make output invisible, which is helpful when a function has a large output, and I'll also cover how to use a function recursively. If your function returns a lot of results, it might be a bit obnoxious when a person forgets to assign the output to an R object. If you think your output is likely to be annoying when it's printed out, you can use the invisible function in place of the return function. Then, when a user fails to save the result to an R object, their console will not be flooded with output. And if they do assign the output to an object, the object will store the result. That said, invisible output can confuse users, so use this trick with caution. It's also worth noting that using classes and methods inside of R is another way to address this challenge. However, classes and methods aren't a topic I'll cover in this video. And one more tip before we move on to recursive functions. If you happen to flood your console screen, or if you simply want to clear the console, if you're on a Mac, use Command-Alt-L, or if you're on Windows, Control-L, which will clear your console screen. Alright, on to recursive functions. A recursive function is a function that may call itself. For example, I can create a function called logMe that takes the log of a value if the value is larger than 1 and keeps doing this until it gets a value that's less than 1. If the value is less than 1, then the function simply returns the result. The way the code is written works, but what if I happen to change the function's name? I would still want the function to call itself. To make sure it does, I should use the function called recall, which automatically calls the function it's in. In general, using recall is the preferred way to build recursive functions in R. In the next video, we'll look at how to use a custom function with the apply function. In the last section, I talked a bit about the apply family of functions. These are very powerful functions for applying the same function across many sets of data. They're even more powerful when combined with custom functions. To begin, I'm going to create a sample object X that's a matrix with 1,000 rows and 10 columns containing 10,000 random draws from a Poisson distribution with 8 degrees of freedom. If you recall, I could use apply to apply a function across each row or column. Here, I've calculated the mean for each column. If I wanted, I could also create a custom function on the fly that calculates the standard error of the mean using each column separately. Note that here I've omitted the braces for the function declaration. I did this since the function can fit on one line, but I could include braces if I liked. This inline use of functions is very useful since it allows you to apply simple custom functions on the fly. It's also common to make complex functions and use them in the third argument of apply. Here I'm going to first load in the getCI function, then I'm going to call it inside of apply. You might recall that the getCI function actually returned a list. The apply function adapts its output to accommodate complex outputs by the function being applied. Sometimes it will return a vector, other times a matrix, and other times a list. Here, since getCI outputs a list, the best way to represent many outputs of that function is to contain them in a sort of superlist. This completes the fourth section of videos. Take some time to try out what you've learned in these first 4 sections of video. Browse online for some data, or access some of these datasets that are already present in your R session.